Question 6.2 says calculate the energy of one photon, okay, of yellow light that has a wavelength of 589 meters. Okay, so if we know that the energy, okay, of just a single photon, we're told has a wavelength of 589 nanometers. Okay, and we know that E is equal to H times V. Okay, and we know that C is equal to lambda times the frequency. So if we plug all this in, okay, we know that H is just equal to 6.626 times 10 to the minus 34 joule seconds. Okay, that's given to you. And so if we plug all this in, we basically get, we have 2.998 times 10 to the 8 meters per second, okay, is going to be equal to the wavelength, which is 589 nanometers, but we need to convert that into meters, okay, and so there's 10 to the minus 9th meters in 1 nanometer, okay, and then we're just multiplying that times the velocity, or by the frequency, okay, and so what we get is that V is equal to 5.089 times 10 to the 14th inverse seconds. Okay, so then if we just plug into this equation where E is equal to Planck's constant times the frequency, okay, then we have E of a single photon is going to be equal to 6.626 times 10 to the minus 34 joule seconds. So joule seconds, okay, and then we're going to multiply that by the frequency from above, 5.089 times 10 to the 14th inverse seconds, okay, and then we can solve for this, so our seconds are going to cancel and we're going to be left with joules, and we get 3.37 times 10 to the minus 19th joules. Alright, so the second part of the question says a laser emits light that has a frequency of 4.69 times 10 to the 14th. What is the energy of one photon of this radiation? Alright, and so if we set this up, just like we did the last question, we know that E is equal to Planck's constant times the frequency. Okay, we know Planck's constant is equal to 6.626 times 10 to the minus 34 joule seconds, okay, times the frequency, which we're given, which is 4.69 times 10 to the 14th inverse seconds, okay, and then we solve for this, our seconds are going to cancel, and what we get is 3.11 times 10 to the minus 19th joules. Alright, part C is basically just saying, using the answer from part B, how many photons are emitted if a laser emits 1.3 times 10 to the minus second joules. Okay, so if we know that we have 1.3 times 10 to the minus second joules, okay, which is the amount of energy from the laser, okay, and we just solved that the energy of one photon, okay, was basically equal to, in one photon, we know that there was 3.11 times 10 to the minus 19th joules, which is just the solution from the last problem. Okay, well, we can solve for the number of photons, which is 4.2 times 10 to the 16th photons.